Hello. Today I'm going to talk about some basic graphs, some ones we haven't talked about in class, and just hit through the highlights. All right, so first is exponential. So here are some examples of 2 to a power, but of course exponential can be 3 to the x, it can be 5 to the x minus 1, it can be a whole bunch of things, But here are some basic ideas. What's important to know about, just looking at like 2 to the x. Well, I know that if I keep, increasing x, so 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, right, it's going to drastically get larger and larger very, very quickly. But when I start plugging in negative x values, remember negative x's, all right, so this one over here, it flips it. So this one right here is basically saying 1 over 2 to the x. So when I start plugging in these negative x's over here, right, we're going to get 1 over some really big number. So we're never going to quite hit 0, even though that's what this graph looks like, but that's called a horizontal asymptote. So right here, the horizontal asymptote would be y equals 0. Okay, because anything raised to a power, it's never going to equal 0. 2 to the x will never, ever equal 0. Okay? And let's see. If I were to change that to maybe say like 2 to the x plus 3, then everything would just shift up 3. So you see I'm at 0, 1, so now I would be at 0, 4. And my horizontal asymptote was at y equals 0. Now it's at y equals 3. So that would be the new horizontal asymptote. Be better than that. All right, hopefully that makes sense. Okay, I know I kind of said a lot there, so I'm sorry if I spoke too fast. All right, the next part about this is I just wanted to show you, let me erase all the blue. Okay, when you have a negative out front, all right, so this middle one right here, when that happens, all right, what that's really saying is negative and then 2 to the x. So basically it makes all your y values are now negative because that negative is on the outside. Okay, so that's where it's flipping my entire graph down. Okay, right, we're going from here and we're flipping it down. Now, when you have a negative exponent, all right, so for this third one over here, now that we're here, we have the negative exponent, remember, makes it a fraction. So now it's, you're flipping it vertically, okay? So we're flipping it kind of across that y-axis, okay? So what's on the outside, it flips down. When it's on the inside next to that x, like in that exponent, right, it's flipping it side to side. Okay, again, if you ever don't know how a graph looks, plug it into your calculator, right? Look at the original, then look at it with a negative, right? You got this. Let's see, logarithms, all right? Notice these look very similar, okay? That's because they are inverses of your exponential, right? So see how this one is going this way, right? Over here, it's going the other direction. So I'm going to write it's the inverse of exponential. And remember, inverse is where y and x are flipped. So if you graph the line y equals x, all right, the inverse, so the exponential graph, remember, looked like this. And you see how they kind of tilt your head, and it's kind of like a butterfly, right? That's what's going to happen, where that blue line is the middle. Okay, just a neat little relationship there. But the log is what we're focusing on. So here, it's going to look like there's an asymptote over here, but there isn't one. This is steadily getting larger and larger and larger. Okay, so there is no horizontal asymptote. There is a vertical one, though, Okay, because remember, we have log x equals y. All right, that's what this graph is. So remember, the base is 10. So if we rewrite it in exponent, 10 to the y equals x. Well, remember, 10 to the y is never going to equal 0. So therefore, x can never equal 0. And then that's why we have a vertical asymptote at x equals 0. Okay, that's the explanation behind it. But again, you can always graph it and find it on your calculator. Okay, so you can use the trace function and just, zoom out like crazy and just see how far it is, or use your tables. Okay, plug in your equation, set your table at like 1,000 to go every 1,000, and just see what happens when you plug in massive numbers. That'll do your horizontal asymptotes. Okay, for the vertical asymptote, I would notice, if you start to trace this one, and you're noticing that the x is getting closer and closer to 0, you can always look at your tables, right? Or just plug in 0 and you'd get an error. Okay? That's the kind of nice part about vertical. You can just plug the number in and it should tell you error. If it doesn't tell you error, then it's not an asymptote. Horizontal, I would use my graphing calculator, the tables for horizontal. Plug in really big numbers. Just massive. Plug in 1 billion. All right, rational functions are when you have 1 over x. So again, they're going to go out to forever, so you can just plug in like a bajillion, right? So for the horizontal asymptote, let's plug in 1 billion. Well, into our graph, that's 1 over 1 billion. That's 1 out of 1 billion. That's practically nothing. Okay? So your horizontal asymptote is y equals 0. Okay? All right. Again, we can trace it. If we want to do our vertical asymptote for a rational function, okay, that's when we have our error, right? 1 over x, the denominator. So the denominator can't be 0. So x can't be 0. So your vertical asymptote is at x equals 0. Okay? I don't like that I did that red. I want it to stand out a little different. We'll change that. Sorry. It makes me feel better. All right. So rational. So those are basically it. So if we think about it, right, if we do a horizontal one here, all right. Essentially, we can plug in 1 billion again, but 1 billion times, let me do the pink. Okay. Horizontal asymptote, plug in 1 billion. So 4 times 1 billion minus 3. That's pretty much 4 billion. Because if I have $4 billion and I lose $3, I'm still calling myself a billionaire, right? Then on the denominator, you have 2 times 1 billion plus 1. So essentially 2 billion. So that's 4 billion divided by 2 billion. That's just 2. So my horizontal asymptote is y equals 2. And notice that's what it is. You do your vertical asymptote. All right, that's where the denominator can't be 0. So 2x plus 1 can't be 0. So you solve this. X can't be, which will be the vertical asymptote, negative 1/2. And notice that's what we have right here. Ooh, I can't really draw perfect, but you get the idea. So that's if, you have the same order on top and bottom. So this was 4x over 2x. And the one before that, that was 1 over x, which you could have even done if we had, x squared over x cubed, right? If the bigger one was on bottom, we can still do this the same way. All right, but we run into an issue when it's like this. So these are special ones. All right, so when it's a larger number on top, so the bigger, so it's x squared over your x. Okay, so x squared over, can't circle that right. So x squared over x to the first. You're going to have something called the slant asymptote. You don't have to know what that is for IB, so we won't worry about it. But you can still get the vertical asymptote. Okay, the vertical asymptote is still when 3x plus 1 doesn't equal 0. And that was a 3. Ooh, that's terrible. Yeah, that's better. So this is when x is negative 1/3, which is what we have. Okay, sorry, I'm trying to go through it fast. Next one, the sinusoidal. Sinusoidal? I don't know if I'm saying that right. Whatever. Sine and cosine. So they are your waves. Okay? Now, basic sine and cosine, they're going to look like this. Sine of x is always going to go through the origin. Cosine x always starts at 0, 1. Okay, so you start on top of the mountain with cosine, and with sine you start at the origin. All right. So real quick, this is really silly, but I always struggled trying to remember which one was sine and which one was cosine. Yes, you can graph it and you'll easily tell, but if you want to just remember it, all right, I remember the song, I Saw the Sign. It's a great classic pop song. It's like 80s, I don't know, it's old. But it's, I saw the sign, it opened up my eyes, I saw the sign. I can't believe I'm singing. Anyway, so that song, well, if you stand at the origin, you're going to see the sign because the sign is going over you, right? But if you are if you're a cosine, you do not see the sign, okay? That's just how I memorized it. All right, things you need to know about sine and cosine. There's something called the amplitude. So this is how high a graph can get. So an amplitude, I like to think of music and waves, amps on a guitar, right? On your, you know what I mean, with music. So how you determine how high something goes, well, look at these graphs and then notice what we have here. How high this is, the amplitude is from the middle of the graph, all right, to the top. So that is the amplitude. Okay, so the amplitude here would just be 1. Okay, for this one, all right, the amplitude for this graph, it's going here all the way up to here, so that would be 3. The amplitude here, well, it's a little bit harder to see, but it's going to be 1/3. Wonder if you caught that. The 3 here is the 3 there. The 1/3 is the 1/3 there. So it's how tall the graph is. It's always the number in front of it. Okay? The period is how many repeats the graph has. So on the original one, on sine, all right, so our period, all right, so when does it repeat? It starts here at the origin, and it repeats right here. So this is essentially like a stamp, and if I stamp it side by side, I can continue this wavelength forever. Okay, where one starts, the other one finishes. Well, I'm sorry, with one finishes, then you can start again. That doesn't make sense. Ask me in class. So on this one, notice it's a little bit past 6. So hopefully if you think about that, if we're on the unit circle and we start with our angle of 0, right, sine of 0 degrees, we can go all the way around the circle for 360 or 2 pi, right? That's your radians. So the period here is it repeats every 2 pi. Okay. So let's look over here. So the period over here, so we're starting at sine at the origin. It repeats, all right, when it comes back up again right here. Okay, so that is, okay, it's like 1 point something. Oh, it's because I thought I picked a nice number. I didn't put pi in there. How you get the period is you do 2 pi over this number in front of the x. So 2 pi over 4. So the period for this one is pi over 2. Okay. For this one, all right, for the second one, we do 2 pi always over what's in front of the x. So we can rewrite this as 1/3 sine of 1/2 times x. So the number we're going to be dividing by is 1/2. Keep, change, flip. We get 4 pi. And notice it's off my graph, right? Because 4 pi is, my goodness, going to be over 12, and that's at 10. Okay, so it's going to be somewhere over here. All right, and that's how you get the period. So just to break it down, and it works for sine and cosine, of course. So we have a sine bx plus d. All right, so a is your amplitude, and then 2 pi over b is your period. All right, and d is kind of where it sits on the graph. Okay, so d is kind of like its up-down shift. Okay, so if I go back to the sine, right, or cosine, if I had, cosine x minus 3, then I would go down, I would just move this whole graph down 3. So we would have, oh goodness, right, it would be down here. Okay. All right, so hopefully that makes sense. Those are your basic graphs. Again, you can always plug this into your graphing calculator and go from there. All right, feel free to ask me any questions. Have a good night.